Today we are explaining single-rollout asynchronous optimization for Agentic reinforcement learning. It asks a practical question. Can an AI agent learn from long-tail using tasks as soon as each attempt finishes, without making training unstable?
Why does finishing one attempt earlier matter for an agent?
Agentic tasks can take very different amounts of time. One coding attempt may finish quickly, while another keeps calling tools. In the usual group-based workflow, the finished attempts wait for the slowest member of their group before training can start. That wastes time and makes the data older by the time the model learns from it.
So why not update immediately after every completed trajectory?
Because the training model has already changed while a rollout is still being generated. That mismatch is called off-policy drift. Group Relative Policy Optimization, or GARPO, also estimates advantage by comparing several responses to the same prompt. With just one response, that comparison disappears and the learning signal becomes much noisier.
What is the paper's alternative to waiting for a whole group?
The method is called SAO, short for Single-Rollout Asynchronous Optimization. Each prompt produces one trajectory. The moment that trajectory is complete, it can enter training. The proposal combines that schedule with a critic that estimates how good the trajectory was, plus safeguards that prevent stale rollouts from causing oversized updates.
The top and bottom schedules look different. What should I notice?
At the top, GARPO collects a group and leaves early completions idle until every numbered trajectory arrives. At the bottom, SAO feeds each finished trajectory directly into training. The right side shows the second ingredient. SAO uses a narrower, two-sided trust region, so both unusually large and unusually small probability changes are blocked. To measure how still a token is, SAO compares the current model's probability for that token with the probability recorded by the rollout engine. This ratio is not guessed from a saved historical policy. It is computed directly from the rollout log, which is useful when many generations are in flight at once.
How does that ratio keep an old rollout from steering training too far?
SAO only accepts a token when its ratio lies between a lower and an upper threshold. The lower bound matters as much as the upper one. A token whose probability has collapsed is also unreliable evidence. The resulting loss weights useful advantages, but masks token updates once the current policy has moved too far from the rollout policy. Single rollout training still needs an advantage estimate. SAO uses a value model, but treats an agent action as the text the model generates between two observations. Its skip observation estimator connects the last token of one action directly to the first token of the next action, instead of letting unpredictable environment feedback contaminate the advantage signal.
Does the value model need special treatment to make that estimate reliable?
Yes. The authors pre-train the value model on more data to avoid a weak cold start. During reinforcement learning, they update the critic twice for each policy update and freeze its attention parameters. The idea is to give the critic a steadier target without allowing its internal attention layers to change so violently that value estimates become unstable.
What tasks test whether those design choices actually help agents?
The evaluation covers for reasoning benchmarks in a setting where the model can use Python, and the SWE bench verified coding benchmark. The comparison is against the supervised starting model and GARPO. On every displayed benchmark, SAO is the highest bar, so the advantage is not limited to one kind of task. The differences are concrete. On AME 2025, on Beyond A, IME it reaches 70 for point 8 versus 50 for point 8. The coding result is smaller but still positive 29.8 on SWE bench verified versus 27.0 for GARPO. Those comparisons support the claim that removing group weighting did not trade away task effectiveness.
Could the gain simply come from the clipping safeguard, rather than from using one rollout?
The training curves address that comparison. GARPO with the same direct importance sampling safeguard improves on a vanilla GARPO implementation, but SAO remains above it for almost the whole IME 25 run. That makes the result more specific. Clipping helps control policy lag, and the single rollout design adds an additional benefit. The stability analysis explains why the safeguards matter. Updating all critic parameters creates much larger critic gradient norms. Freezing attention keeps those gradients lower and smoother. And without the direct double-sided clipping, a VAPO baseline leaves almost every token unclipped, fails to reject divergent off-policy updates, and collapses at roughly 90 training steps.
What happens when the target behavior changes while the agent is learning?
The authors simulate that setting with a writing task. The reward preference changes over time among styles such as Qt, ShuUni-BU, and Classical. Because only one trajectory per prompt is available, a group relative method is a poor fit. SAO's critic can still provide an advantage estimate from the individual trajectory. In that simulation, SAO rapidly relearns after each reward change, shifting toward the style currently preferred by the environment. This matters beyond the toy writing task. Online systems often receive feedback one trajectory at a time and face changing objectives. Exactly the setting where waiting for a matched group is least natural.
Are there other simple ways to use a single rollout?
The appendix compares SAO with the running mean reward baseline Handeskio. Those alternatives rely on prior information about how difficult each training prompt is, and they perform worse. It also tests step-level value estimates, such as averaging values within an agent turn. Those versions underperform token-wise value training, which gives the critic a finer-grained signal through complex reasoning traces. The main limitation is also clear from the design. SAO depends on a well-trained value model without a strong critic. One rollout has a high variance learning signal. The paper therefore shows a recipe for making asynchronous learning stable, rather than claiming that a single trajectory is automatically sufficient in every environment.
So what is the final result to remember?
SAO replaces slow group-wise sampling with immediate single rollout updates for agent IC reinforcement learning. It controls stale data with direct double-sided importance sampling, estimates advantages across two observations with the value model, and beats GARPO across the reported reasoning uncoding benchmarks while remaining stable for 1,000 training steps. That is the paper's central case for asynchronous agent training.
Thank you.
That wraps up our paper explanation.